Hardness, by definition, is the ability that one material has to permanently deform another. Hardness, in a very vulgar English jargon, is also defined as the ability that one material has to scratch another. The moment you create a scratch, that immediately represents plastic deformation. That's why whenever you use hardness, you are looking for the change in that surface created when you take an indenter. In this case, the indenter will have a cylindrical shape and a spherical shape. You apply a force, you generate an indent of a given diameter. That indent depth, that indent diameter is used to calculate what is the relative hardness of the material. So, as you increase in hardness, you need to change the nature of the indenter. The harder the material it is, the stronger or harder that indenter must be. So one of the most common scales that we use for surface hardness measurement, that means macro hardness measurement, is taken from the surface of the material, is the Rodwell hardness testing. These days, those units are running between $6,000 and $8,500. That's a significant saving compared to $50,000 minimum investment for a stress strain testing rig. And they are fully digital, meaning you don't have to take that sample, bring it to microscope, determine the depth of the indentation, determine the diameter of the indentation, and calculate the relative hardness. Already the machine will give it to you. And now you don't even have to think or do any significant process changes to the measurement when you translate from one scale to the other. In the Rodwell harness testing procedure, you have different choices of indenters, all going, all of them have been identified by letters, from A all the way to F. In the material selections that we have for structural applications, the most common scales will be the B and the C. And the beauty of the Rodwell harness testing is that already the American Society for the Testing of Materials is allowing you to translate the Rodwell into the Brinell harness, which is another scale, and the Brinell harness can automatically be transformed into the ultimate tensile strength. So by just doing a transformation that is handled by just looking at a chart, because there is a correspondence from Rodwell B and C to the Brinell, you get the Brinell harness multiplied by the appropriate factor, and you can report the maximum strength of that material either in imperial units, PSI, or in metric units, megapascals. So hardness is a very simplified approach to categorize materials based on their maximum ultimate tensile strength. The indenter shapes vary from going to soft materials where you are using hardened steel to what we call a braille that has a conical shape, and that cone is impregnated with diamond. So I mentioned to you our preferred scales are going to be the B and the C within the Rodwell. For the B, you will use a hardened steel sphere, and for the C, you will use the impregnated diamond braille. Diamond is the hardest element on Earth, is an ISO um, is a lotriopode of transformation of carbon. Diamond is just carbon. Diamond actually, by thermodynamic definition, is a metastable compound. That means eventually, after many millions of years, all those beautiful diamonds you are giving away when you engage to somebody are going to reverse back to just what it is, carbon. But that takes time. So B and C are going to be your scales, and this is what we're going to be doing continuously as we measure and evaluate strengthening methods in the materials lab if you decide to join that materials lab next semester. Remember, to be able to join that class, you have to have a minimum grade of C in the 207 in order to be admitted into the materials lab. So, when we began this lecture, I talked to you about engineering and true stress. The difference between engineering and true stress is just the way the stress and the strain are calculated to generate the stress strain curve. In the engineering stress strain, remember, for stress, we use the original cross-sectional area of the sample prior to any deformation. And for the strain, we always make that deformation calculation with respect to the original length of the sample. In the true stress strain curve, what is meant by that is, as you apply the load, you begin the calculation of your stress based on the load that you're applying, but also you take into account the instantaneous change of that cross-sectional area and the instantaneous change of that original length. You know that under the limitations of the design of the testing rig, that becomes extremely expensive to adapt sensors to that machine to allow us to be measuring continuously as you deform the material, both the cross-sectional area and the length. It can be done, but it will make the test rig more expensive than it is today. But we don't worry about it, because I told you that during deformation of solids, the primary assumption you're always going to do, and in reality it remains in the solid state, is that the volume of the solid remains constant. With that assumption of constant volume, we can translate engineering stress and engineering strain into true stress and true strain. And that will be part of the exercise that I will be posting into Blackboard on Friday, that is due on Monday for you guys. You're going to show me how do you calculate true stress and true strain from knowing engineering stress and engineering strain with the assumption of constant volume. It's a very nice, simple, mathematical, mental exercise that I want you to do. The only reason why the true stress and the true strain is used is because, remember that I told you, since hardness is a surrogate of strength, we can make some of these non-ferrous alloy stronger by simply applying plastic deformation. In order to identify how amenable is one kind of material to become hardened by simply plastically deformed, you need to know the correlation between true stress and true strain to be able to calculate the hardening exponent N. I will walk you through an exercise next week once you give me that calculation or derivation of true stress and true strain as a function of engineering stress and strain. I will give you an exercise that we're going to work together in order to calculate from that knowledge of transformation the hardening exponent. This particular question is usually 10 points, and it is associated to that question that you were analyzing last time in class when we were looking at a stress strain engineering diagram and dissecting from that diagram all those 7 mechanical properties. After you know how to translate from engineering to true strain, then there is an additional calculation you need to make, which is defining the straining or hardening exponent. This will allow you to make a judicious choice whether it is worth to spend the effort in hardening a non-ferrous alloy by plastic deformation. Because every decision that you make in engineering, whether you like it or not, it has a cost. And your function is to minimize that cost to your employer. As an engineer, you are a solution seeker. As an engineer, you are a solution optimizer. As an engineer, you are simply a bean counter saving money to your employer. Your value will depend on how good are you at saving money for your employer. So as a summary, stress and strain, these are two parameters to express the mechanical behavior of any material. Stress will be the force that you need to apply divided by the surface area perpendicular to that force. Comes in units of megapascals or pascals for the metric system, newtons over meter squared. Strain is a measurement of the deformation that is created once you subject that component to either a compressive or a tensile force. Is totally dimensionless as long as you maintain consistency of units in the denominator, which represents the change in that original length divided by the original length. It doesn't matter whether you do it with metric or imperial units. Elastic behavior is all about the ability that material has to allow for the stretching of the bonds. That stretching of the bonds is related to the nature of the bonding. So by knowing what type of material you have, you can predict how easy it is to stretch that material. Elastic behavior also represents no permanent deformation. So as long as you don't exceed the yield point, which is the level of stress infinitesimally higher than the elastic or proportionality limit, your material will restore to the original dimensions. Plastic behavior, to the contrary, your deformation will remain permanent. Plastic deformation will lead to a strengthening of the material, and plastic deformation is only possible because you have the dislocations as defects in your steel or material bulk. By plastic deformation, the moment you reach that regime of deformation, there is always a component that is tangential to the force that you're applying, that will be the force required to activate your slip systems, that will let your dislocations move and multiply, and that will make possible for you to execute plastic deformation. Toughness, remember, it is the energy that is required to break a material or to initiate the onset of necking. Remember, toughness is calculated with plastic deformation. Ductility is how much can you deform plastically that material. that is why defined as the plastic strain at failure. But it's only plastic strain. So when you do this calculation, you need to eliminate any contribution from elastic strain. Any
Professor,
questions regarding this material before we move on?
I have a question.
Yes, Mr. Hernandez.
Remember when we were hardening materials and we were shifting um, the modulus of elasticity to the right? Does that also decrease its toughness because we're reducing the area under the curve?
Yes, anything that decreases the area under the curve, that will decrease the toughness of the material. For
So,
next class, I will also bring you an exercise where you are going to tell me, based on how those strain curve look like, what are the trends in terms of elasticity, toughness, ductility, and maximum strength. That will give you a better appreciation from analysis of this curve, how to make predictions from one material to the other by just looking at the stress strain diagram. Okay? I just don't want to generalize anything for you. I want you to see it from experimental data, and then you will make your own understanding. Okay? Any questions regarding stress, strain, and strength of materials? Very good. So let us move to the next. We're going to stop and we're going to share again. So remember that I told you that the primary reason why materials are chosen is because of their level of strength. I say primary reason, meaning most of the time that is what actually decides what material you're going to use for a given application. So there are 4 different strategies that we can use to strengthen a material. And the first one, and I hope is the one that you can really appreciate relatively easily, is by changing the grain size. Remember, when you have a solid, in particular, if you are dealing with a metal or an alloy, that solid is going to be composed of an arrangement of grains. All these grains were developed during the process of solidification in that material. And you know that the grains that are closer to the mold material where the liquid is solidifying will form with a finer grain structure than the ones that are forming from the inside of the molten pool, because there is a larger path for the heat transfer. So heat is withdrawn slower from the center of the mold toward the edge of the mold. That will define whether you have a fine grain or a large grain structure. So whether your structure is fine or larger in terms of the grain size is going to be critical in order to define which one of the material types, the fine or the large grain, is the stronger. So when we talk about strengthening, remember, strengthening processes are designed with one single issue in mind: to stop the movement of dislocation. Any restriction to the movement of dislocation will result into a stronger material. If I take that into account, I know that in between grains, you have grain boundaries. The grain boundaries are created at those points where the different grains that are growing in completely different directions will come together. That discrepancy between one orientation and the other leads to the formation of the grain boundary. You know that the grain boundary, then, if there are two interfaces meeting, it means it is a surface defect. The finer the structure it is, the more impediment to the movement of the dislocations you are creating. Remember that dislocations only move within the grains. Every time you cross a grain boundary, there is an effort that needs to be applied. That effort is you need to put more force to make sure that that dislocation keeps on moving past that grain boundary. So the finer the structure, the more the grains you have, the more the number of grain boundaries, the more effort, the more force you need to apply in order to move the dislocations.
Professor,
Yes, sir.
does that translate in more energy being stored by the material?
Yes, because it is going to translate into increasing your levels of strength. Your yield strength will increase, your ultimate tensile strength will increase, and you may decrease or increase your ductility. So at the end of the day, any impediment to the movement of the dislocations in order to create the plastic deformation, because plastic deformation doesn't take place if the dislocations do not move, the stronger the material will become, the more impediment you create. That means the more energy you require to break or neck this material. So usually grain size manipulation is not the most effective way to get you the level of strength that you require, but it provides an approach. And it's much better than simply forming solid solutions. Pure metal elements are extremely weak. What motivates us to create alloys is to put another element into that structure that, because of the size difference, because of the electronegativity difference, because of the valence electron difference, and because of the relative electronegativity, will create an impediment to the movement of the dislocations. At one point, I asked you when we were looking at the phase diagrams. Remember, you have two types of phase, actually three types of phase diagrams. You have the phase diagram corresponding to interstitial atoms. You have the phase diagram corresponding to an isomorphous alloy. In an isomorphous alloy, you are obeying the 4 rules for full miscibility. And remember that isomorphous phase diagram has the shape of a cat's eye, telling you that in the solid state, you form a complete solubility of one atom on the other. But then you have these other phase diagrams that show limited solubility, meaning in the solid state, you have different phases that can be formed as a function of composition. At that moment, I ask you, which type of alloy, the isomorphous or the limited solubility, has the largest strength? The limited solubility. Why is that? Because the limited solubility has violated any of the 4 rules, and the most likely rule that violated, because it's the most important, is the atomic radii difference. When you form a limited solubility alloy, that means that the atom that you are using to replace the host metal element is going to be definitely larger than the one of the host material. That change in size is gonna create, when you try to put it into that alloy, a strength field that is going to become an impediment to the dislocations. Anything that can impede the moment of the movement of dislocation will increase your strength. So by simply alloying your material and by choosing wisely what level of strength you want to get, you are going to choose whether you're going to make a limited solubility, which will give you the largest strength, because there is going to be a larger difference between that atom size and the atom size that are surrounded. So it's going to create a distortion in the lattice that is going to promote impediment to the movement of those dislocations, as compared to choosing an element that is smaller or the same size, like in an isomorphous alloy. So a limited solubility alloy will become stronger than an isomorphous alloy, simply because the distortion in the lattice is more significant the greater the difference in atomic radii between the alloying element and the host element. So what do you think? Is the creation of the alloy as compared to the grain refinement of the alloy a better approach to strengthen the material? Which of the two processes will give you more for your effort? Refinement of the grain or alloying? Which one is going to give you the greatest impediment to the movement of the dislocations?
I think adding the impurity.
You believe that? Why do you think so?
I feel like it'd be hard to control grain size, especially in a mold, because you kind of can't really control it as far as the center of it being forming larger grains. But this one seems a little more straightforward, where introducing a larger impurity would result in higher strength and more restriction.
From the engineering point of view, which one is less flexible? Which one gives you more freedom as an engineer? To change the grain
I think
size?
the bigger one's less flexible.
Which one?
The larger one.
Right, but which approach? Creating an alloy versus working on the grain size of the material. Which one gives you less flexibility?
Working on it.
Working on it? What do you mean?
Work hardening, like if you were to make raw
no,
iron.
you're going forward. One moment. No. We haven't talked about that yet.
Oh, okay. Sorry.
I am giving you a choice between making an alloy and refining the grain of the alloy. Which one, from the engineering point of view, will give you the best outcome from your effort?
Refining the grain.
Refining the grain.
Yeah.
Do you understand why?
Yeah. You can make
Because
it real.
Refining the grain allows you to manipulate your biggest ally, which is temperature.
Yeah.
And you can change the grain size by introducing intermediate processes of plastic deformation, for example. You won't be able to understand it until we make it in the lab. But you get more manipulation flexibility as an engineer. Remember, an engineer is a creator. An engineer is always looking for something that is tangible, something you can control, something you can modify. That is materials engineering. Creating the alloy, the flexibility is limited simply to maintaining the diameters of the both atoms that you're using, or the number of atoms you're using for your alloy. But it doesn't give you that much flexibility. It locks you there. The only thing you have to play with is the atomic radii and the formation of intermetallic phases.
So this is assuming that cost is not relevant, right?
Yes, for the
Okay.
cost involved, if your objective is to make the material stronger, alloying will be the one that will give you the least benefit for your effort. It
Got
will be followed by Haya. Do you know which process follow?
I got distracted and missed that part. I'm sorry.
So forming a solid solution is at the bottom of your strengthening processes. At the bottom, because it doesn't give you that much engineering flexibility, and it's not going to give you the biggest increase in strength by just alloying. So on top of solid solution, you are going to have grain refinement. Grain refinement will be more effective engineering-wise, manipulating the process to control the grain size, to control the strength of the material. But there is a process that will exceed the expectations of grain refinement. It's very typical for all the alloys used in aero engineering.
Work hardening.
No, that's at the top of the food chain.
Okay.
It's going to be precipitation strengthening. How you achieve this? You need to either introduce a second phase into the structure of your alloy, or you are going to manipulate the phase diagram to create a process that allows you to generate a second phase within the grain of the structure of your material. Remember, these locations move through the grain of the material. You want to put any impediment to the movement of the dislocation, and you want that impediment to be right up the grain structure. So you add a second phase like silicon carbide in aluminum or iron. That precipitate of silicon carbide, you want it to be homogeneously dispersed within the grains of the structure. You're going to use heat for that. You are not going to allow deformation of that component, which you know is going to be harder than iron over aluminum to be formed at the grain boundaries. You don't want hard precipitation formed at the grain boundaries. That, instead of strengthening your material, is going to weaken your material. So you want the precipitate to be formed right within the structure of the grain. So as the dislocations move, in order for you to keep on deforming the material, it means that this location has literally to split that precipitate in half or destroy the precipitate as it moves. Otherwise, you don't get that strength.
Professor.
Yes.
So, that example back there, I thought about it like a road. So would that be like introducing stop signs at a road?
Yes, you're a student, or whenever you are driving, for example, when they install those white things to define the lines in between the lanes in the highway, or at the edges of the highway, in order to tell you you are not paying attention and you are getting off the highway and your car begins to go over a very bumpy road, that is going to slow down your movement every time you hit one of those.
So they would be more like speed bumps than stop signs.
That is speed bumps and stops. Mm-hmm. So, for example, in aluminum alloys, is very practical to strengthen the alloy. This is a grain boundary. That's another grain boundary by promoting the precipitation of second phases within the grain. Each one of these is a precipitate that is forced to be formed inside the grain. So when the dislocations move, you will need to apply more energy in order to promote any deformation. So you are making the material stronger. Remember, strengthening is all about creating impediment to the movement of the dislocations. The last method is what David Love is going to be called work, or known as strain hardening. In cold work and strain hardening, there are 4 basic processes: forging, rolling, extrusion, and drawing. All these processes have in common compressive stresses leading to plastic deformation. All of them are going to result in a decrease of the original cross-section of the material that you are forging, drawing, rolling, or extruding. That plastic deformation is going to generate plastic strain and deformation into the grain structure that is going to create that impediment to the movement of the dislocations. And that process is normally referred as cold work, because you can achieve this with the majority of the alloys that are amenable to straining. Remember, when we draw the true stress, true strain diagram, you will be able to calculate the strain hardening parameter M, so you will be able to make an assessment of how amenable to deformation or strengthening by plastic deformation that material will be.
Professor, don't mean to cut you off, but we're past 10.
Yes, give me just one more minute. So when you do a strain hardening, you begin with a homogeneous distribution of grain structure. When you are done with that, those grains has been elongated in the direction of the cold working process. This is what is going to get you that strengthening. So I will be posting that set of exercises that I want you to work over the weekend. We're going to go over those on Monday.